everyone, and thank you for joining us for this tech transfer webinar on rotorcraft noise abatement presented by inventor Noah Schiller. Noah Schiller is a senior research engineer in the structural acoustics branch at NASA Langley Research Center in Hampton, Virginia. He has advanced degrees, both MS and PhD, in mechanical engineering from Virginia Tech, and has worked on noise and vibration control technologies for the past 15 years. He is a member of the Vertical Flight Society, abbreviated VFS, American Institute of Aeronautics and Astronautics, AIAA, and American Society of Mechanical Engineers, ASME. He is a past chair of ASME's Noise Control and Acoustics Division, has authored or co-authored more than 50 papers, and holds 2 patents with an additional 2 patents pending. My name is Christina Campen, the marketing rep for Langley Research Center, and I'll be your host for this webinar. Following the technical presentation, I will chime back in to give a short presentation on how NASA licenses technologies to outside organizations such as your own. Before we get started, I'd like to ask everyone, please keep their microphones muted, and if you have any questions, please type them into the chat box and we will answer them during the Q&A session at the end. So at this point, I'm going to turn it over to you, Noah.
Okay, great. Thank you, Christina. Okay, so again, my name is Noah Schiller, so I'm going to be giving the presentation, but it's certainly not something I worked on alone. So before I start, I just want to acknowledge the contributions of Nicholas Wadney, Kyle Pashoni, and Stephen Rizzi. And so what I'm going to talk about is the technology we developed, which is phase synchronized multipropeller system. And it has the potential to reduce the noise of the blade passage frequency for certain types of vehicles. Okay, so I'm going to start with some background information. I'll talk about current or conventional systems. I'll present our technology, describe some of the experiments we've conducted to assess the benefit, and then discuss some of the predicted benefits for different vehicle configurations. And finally end with a short summary and then turn it back over to Christina. Okay, so NASA Aeronautics supports advanced air mobility, which is really a vision for a new air transportation system that's able to move people and cargo in new ways, really between places that haven't traditionally been served by aviation. So this new market includes both rural and urban operations. It encompasses different missions, including public transportation, so like air taxi services. It includes cargo delivery, so like delivery drones, for example, and it also includes emergency response, so supporting firefighting efforts and search and rescue, medical transport, things like that. So NASA's role is, we're really trying to help enable this market. And so we're hoping to do that by developing tools and technologies to overcome key market barriers. And community noise is considered to be one of those key barriers, particularly for operations in urban areas. Okay, so advanced air mobility is going to require new types of aircraft. Probably electric or hybrid electric that can take off and land vertically, perhaps similar to the ones that I'm showing here. So the vehicle configurations that are being proposed are really quite diverse. But one thing that they have in common, most of these vehicles have multiple rotors or multiple propellers, and often they're driven by independent electric motors. And so the technology I'm going to talk about is focused on noise, and it was really developed with these types of vehicles in mind, really vehicles with multiple rotors or propellers. It could, theoretically be used on any of the vehicles that I'm kind of showing here, but really the benefit is configuration dependent, and so I'll talk to that as I go through the presentation. Okay, but before we kind of get to the technology, I think this is a really useful graphic for a couple of reasons. It's taken from a recent paper describing urban air mobility noise, and I'm including the reference down at the bottom of the slide. So it's showing potential noise sources on advanced air mobility vehicle. And so I'm not going to, spend time describing these, potential sources, but what I do want to point out is that the dominant sources are going to vary based on the vehicle design and on the operating conditions. And so when you're thinking about noise, there really is no silver bullet, right? There's no single solution that's going to work for everybody. Noise control is really a combination of good design along with specific vehicle technologies that can reduce certain noise sources. And so, with that in mind, the technology I'm going to talk about is focused exclusively on thickness and steady loading noise. It's really intended to reduce the tonal noise specifically at the blade passage frequency. And so, I think of it as like, kind of one piece of a larger puzzle with regard to noise control. Okay, before I talk about kind of the details, I want to give a quick comparison of two different multi-propeller systems. So a conventional two-propeller system and then our technology, so a phase synchronized two-propeller system. So the results I'm showing here they correspond to a specific configuration that we tested in the laboratory. The results are configuration dependent, so the purpose of this slide is just to provide an example of the type of benefit that you can expect with this system. So both the conventional system and the phase synchronized system both use the same propellers. The propellers are spinning at the same rotation rate, and kind of as you'd expect, right, the two systems generate the same thrust. But what's different is the tonal noise specifically at the blade passage frequency. So using the phase synchronized system, you're reducing the overall level of the tonal noise by, in this case, close to 6 dB. And that's an average reduction when you account for radiation in all directions. And so, this is achieved without amplification at other frequencies. And again, there's no thrust penalty. Okay, so I'm going to talk about the technology, certainly in more detail. I'll talk about the specific tests where we collected this data. But before I do that, let me talk about what I mean by a conventional two-propeller system. Okay, so on most vehicles, the propellers are not going to be synchronized. So that means they're not necessarily going to be spinning at exactly the same rotation rate. So, even if your vehicle uses blade pitch, for example, to control attitude, right? You might be using different electric motors for each propeller. And so you're going to have some variation in the nominal rotation rate between the motors. There are cases, if the sets of propellers are driven by a common drive shaft, for example, or you've explicitly included an additional control loop specifically to synchronize groups of propellers, then this may not be the case. But on most systems, the propellers are not going to be spinning at exactly the same rotation rate. And on top of that, neighboring propellers are often configured to spin in opposite directions. And so that's what I'm showing here. So we're looking at the acoustic pressure at the blade passage frequency on a hemisphere below a couple of propellers here. So in this case, we're considering a couple of propellers from this octocopter shown on the left. And we're looking at the isolated propellers here and here. I hope you can see my cursor. And then the combined response on the right. So these two propellers are spinning at a slightly different rotation rate. And so if we look at the pressure time histories down here below, right, T1, the period for propeller 1 is slightly different than the period for propeller 2. And so because of that, you get this kind of interesting interference pattern over here on the right. And this interference pattern is changing with time. All right, so if we look at a specific observer location on this hemisphere, right here, for example, and we look at the pressure time history down below, you can see that the amplitude of the response varies with time. And again, that's because the relative phase between these propellers is constantly changing because the rotation rate is slightly different. And so initially, in this case, you have constructive interference, and so you have some amplification of the signal, and then you have destructive interference where it's attenuated, and that repeats. You know, acoustic pressure is instructive, but really sound pressure level is typically what we care about. So in this case, we're looking at sound pressure level again for the individual propellers on the left and the combined two propeller system on the right. Again, you can see kind of the time varying nature of the sound pressure level in the combined plot. So, you know, in this case, you get attenuation in some regions in exchange for amplification in others, and that pattern is just slowly rotating. Another way to look at these results is to look at the long time average. So if we look at the kind of time averaged sound pressure level, so this is averaged over many propeller revolutions, you get the, you know, kind of as you would expect, right? So the time average response is higher everywhere by about 2 to 4 dB. And that makes sense, right? So now you have two propellers instead of one. But this increase from a single propeller to two propellers, it isn't perfectly uniform everywhere. So if we want to further kind of simplify this comparison into a single number, what we can do is we can look at something called radiated sound power. So you can calculate radiated sound power by integrating the normal component of acoustic intensity over a surface. And so that's what I'm depicting here. It's essentially looking at the response averaged over the entire surface. And in this case, the results are pretty intuitive. So when you add a second propeller, you're doubling the acoustic power, and that means the radiated power goes up by 3 dB. Okay, so now let's do this differently. So let's talk about phase synchronized propellers. And so more specifically, what we're proposing is that you synchronize sets of propellers, or you specify groups of propellers, and then you synchronize the propellers within that group. And so what I mean by synchronize is I mean the propellers within the group need to spin in the same direction and at the same rotation rate. And then we're going to fix the relative angular orientation, or the relative phase, between each propeller in the group. So in this example, we're showing two propellers. They have two blades, and they're offset from each other by 90 degrees. And so what we're proposing for this octocopter, for example, is that you would have 4 separate groups. So the rotation rate of each group could be different, and the rotation rate can even be time varying. But what you want is you want to lock the two together so that you fix the relative angular position between propellers within a group. And I guess I'll come back up here to the figure on the top. In this particular example, since these propellers only have 2 blades, the optimal angular offset is 90 degrees. So you want one propeller to be 90 degrees offset from the other at all instants in time. Okay, so that's what we mean by phase synchronized. So if you do that, right, so what's the benefit? Okay, again, we're going to start by looking at acoustic pressure. In this case, right, so the propellers are spinning in the same direction, and they're spinning at the same rotation rate, and they're offset from each other by 90 degrees. So if we look at the combined response on the right, and we look at the pressure time history at a particular observer location, you can see that you do have, in this case, destructive interference. So the amplitude is reduced, and you don't have that time modulation that you saw in the previous plot. And you don't have that because the relative phase between these propellers is fixed. Okay, so now if we go from acoustic pressure, and instead we switch over and we look at sound pressure level, so you can see that there are directions where you really get significant attenuation, and there are directions where you get slight amplification. If we compare this to our previous plot, so the conventional 2 propeller system, you can see that if you compare the phase synchronized 2 propeller system to the conventional system, you're getting a reduction nearly everywhere. So Now, if we go to, we want to simplify the comparison further just to a single number, we can again go to radiated power. And so here's the comparison, again, kind of averaged over the entire hemisphere. So it's kind of the average difference. And so what we're seeing here is that when you have the two propeller phase synchronized system, it radiates half the acoustic power of just a single propeller. So that's 3 dB less than a single propeller, or a quarter of the acoustic power, 6 dB less than the conventional two propeller system. And that's kind of averaged in all directions. And so that's interesting because, right, it shows that, adding a second propeller, you can increase the thrust of the system, and you can simultaneously reduce the radiated acoustic power at the blade passage frequency. So I have this, asterisk here, right? Because I do want to point out that the benefit is configuration dependent, and I will come back to that in a few slides. But before I do that, I want to talk about, the potential vehicle level benefit of this technology. Okay, so we're going to consider the octocopter again. And so we're assuming this vehicle is hovering 10 meters above the ground at the origin in this figure on the right. So this figure on the right is showing the change in the sound pressure level on the ground at the blade passage frequency when you go from a conventional octocopter, where all 8 propellers are unsynchronized, to this system where you have groups of synchronized propellers, so pairs of synchronized propellers. So in this case, based on our predictions, the reduction would be nearly 4 to 5 dB everywhere on the ground, or nearly everywhere on the ground. Okay, so this was based on predictions. We have, at this point, experimentally assessed several different multi-propeller systems to really assess the accuracy of our predictions. So we've looked at systems both in hover and axial inflow. So in one case, we've synchronized the propellers mechanically using a drive belt, for example. In other cases, we've used separate electric motors, and we've synchronized them electronically using a separate control system. Really, all the tests so far, as you might notice on here, we have been using relatively small propellers. But again, what we were really trying to do here is to confirm that the predictions accurately capture the effect. So once we're confident with the predictions, then we can use them to evaluate other systems and other configurations. Okay, so I'm going to talk a little bit more about one of the tests we conducted. And so here I'm showing a test setup. This test was conducted in one of our anechoic chambers. So for this one, we had a static array of 5 microphones. The test article was situated in the center of the anechoic chamber on a turntable. So the way we conducted the test is we spun up the propellers. We collected data. We then turned the propellers off, and then we repositioned the two propeller system. So we rotated it by some angle, and then we turned the propellers on and conducted the test again, and then we repeated this. And in the end, we ended up with measurements around this entire hemisphere. Okay, I guess I should go back. I neglected to point out that we also had a load cell beneath the test article, so we could measure thrust, and we also had a laser tachometer, so we could measure the rotation rate. Okay, so in the end, we ended up with 155 different measurement locations distributed on the surface of this hemisphere, and so that allowed us to determine directivity and to estimate radiated sound power. Okay, and so here are some of the results. And so we're looking at the sound pressure level at the blade passage frequency at different measurement locations around the hemisphere. All right, so really we're looking at polar plots of sound pressure level is in the radial direction, and the sound pressure level at different azimuthal locations around the hemisphere. Okay, so these top 2 plots correspond to microphones positioned in the plane of the propellers. So they're denoted here in blue. These bottom two plots correspond to the microphone locations 45 degrees below the plane of the propeller, so negative 45-degree elevation angles. The two figures in the middle correspond to the conventional two-propeller system. The figures on the right correspond to the phase synchronized system. Okay, so you can see that there is a pretty significant change in the directivity when you use the phase synchronized system. So you go from, the conventional system radiates somewhat uniformly in all directions. The phase synchronized system radiates more like a dipole. You get this figure 8 pattern. But you also get a significant reduction in the levels. But what's more important here is that the predictions, which are the solid lines, match reasonably well with the measurements, which are the open red circles. Certainly, the predictions capture the relevant trends, which is good. Okay, so we also process the data in order to calculate radiated sound power. And so that's what I'm showing here. So on this table, everything is normalized relative to the conventional two-propeller system. So that's our baseline. That's shown in the middle. Okay, so if you start here at the conventional two-propeller system, you take away one propeller, right? You have a reduction in the thrust by a factor of 2. You also have a reduction in the acoustic power by a factor of 2. So it's 3 dB down. If you compare that to the phase synchronized two-propeller system, so in this case, you have no change in thrust, but you have a close to 6 dB reduction in the radiated acoustic power. And I should point out that that's pretty close to the predicted benefit. So again, that gives us additional confidence in our predictions. But again, right, we have this disclaimer at the bottom that the benefit is configuration dependent. So, what does that mean? Okay, so now I've shown you that the predictions and measurements agree reasonably well. So we can use those predictions to evaluate other vehicle configurations, other operating conditions, to really understand the limitations of this approach. Okay, so what I'm showing here is I'm showing a configuration with two propellers, and they're separated by some distance d, and rotating at some rotation rate omega. So based on those two numbers, you can use a couple of simple equations that are shown in the rectangular box there. And you can calculate the blade passage frequency and the acoustic wavelength at the blade passage frequency. It turns out that the ratio of the propeller spacing relative to the acoustic wavelength is really what's important. I mean, that controls the overall benefit that you're going to get of this technology. It turns out that you can only get significant attenuation in the radiated power when that ratio is less than 0.5. Ideally, you want it to be as small as possible. So this figure on the right, it's showing radiated sound power, or change in radiated sound power relative to a conventional system as a function of this ratio of d over lambda. So the circle here corresponds to the experiment that I just talked about, right? So in that case, we had we were roughly 0.2, and we got a reduction in the radiated sound power of approximately 6 dB. So this curve is useful because now we can look at what the impact of changes will be. So for example, if we keep everything else fixed and we just increase the separation distance between the propellers, you can see that you get a reduction in the benefit, right? You just increase the separation distance, you're going to move to the right along this curve. Or if you just, for example, increase the rotation rate with everything else fixed, if you increase the rotation rate, you're going to be decreasing the wavelength, and again, you're going to be moving to the right along this curve. And so you're going to get a reduction in the overall benefit. So, the takeaway here is that you really want to be as far to the left as possible. Okay, so so far I've really only talked about the octocopter. I just want to briefly show a couple of other types of vehicles and notionally show how you could define phase synchronized groups of propellers on those types of vehicles. So this technology is not limited to just two-bladed propellers, and you're not just limited to groups of two. Okay, so in this case, we're looking at a vehicle that has 3 propellers along each side of the main wing. And so what you could do in this case is you could synchronize all 3 propellers on each side of the main wing. So if you do that, right, the curve here looks a bit different, but the takeaway is still the same. So the takeaway is you still want this ratio of the hub-to-hub spacing relative to the acoustic wavelength to be significantly less than 1/2 to get a significant global reduction in the radiated sound power at the blade passage frequency. A couple other points I want to make on here. So in this case, in this figure on the bottom, I'm showing 3-bladed propellers. So if you have 3-bladed propellers arranged linearly like this, then you'd want them to be offset from each other by 60 degrees. The concept vehicle is showing 5-bladed propellers. So if you have 5-bladed propellers, so in that case, you'd want them to be offset from each other by 36 degrees. So it's really the optimal offset is simply 180 divided by the number of propellers when they're arranged linearly like this. But they don't have to be arranged linearly. So on this type of vehicle, you could again have groups of 3, but the propellers in this case are not arranged linearly, but they could be arranged at the vertices of an equilateral triangle, for example. And so when they're arranged in this type of configuration, if you have groups of 3 and they're 2-bladed propellers, then your optimal offset will be 60 degrees. And I think it's kind of interesting if you look at the predicted benefit, the change in radiated power versus this ratio of hub-to-hub spacing over the acoustic wavelength. This curve is identical to the one that we saw previously for groups of 2. And so, again, the takeaway is still the same. You want to be as far to the left as possible. So with that, I'm going to wrap up. So I've shown that phase synchronized multipropeller system has the potential to reduce tonal noise at the blade passage frequency. Again, the system requires that groups of propellers have a common rotation rate and rotation direction. And they need to have a fixed angular phase between each propeller in the group. In terms of limitations, so the propeller spacing needs to be small relative to the acoustic wavelength, really to achieve significant global attenuation. And I just want to close with something I said earlier, right? So there's really no one-size-fits-all solution. Noise control requires good design first and foremost, but it can, certainly vehicle technologies can help. And this is one technology that can help in some applications. And so, again, I see this as one piece of the larger puzzle when you're thinking about vehicle noise. And with that, I am going to turn it back over to you, Christina.